The next logical step is to look at a multi-channel queuing system in which two or more servers or channels are available to handle arriving customers. Let us still assume that customers awaiting service form one single line and then proceed to the first available server. An example of such a multi-channel single-phase waiting line is found in many banks today. A command line is formed and the customer at the head of the line proceeds to the first free teller, just like this. The multiple channel system presented here again assumes that arrivals follow a Poisson probability distribution and that service times are distributed exponentially. Service is first come, first served, and all servers are assumed to perform at the same rate. Other assumptions listed earlier for the single channel model apply here as well. Notice that this MMM model has not only lambda and mu, but also m right here, which is number of channels open. Here are the formula for the multi-channel model. They look much more complex than MM1 model, yet they are used in the same fashion that we used in the MM1 model. Let us look at the actual calculation together in the next slides. Here is an Arnold's muffler shop. In previous session, we thought about the impact of hiring a mechanic with a higher efficiency. Now the owner Arnold is thinking about hiring another mechanic that has the similar ability as the current mechanic has. In other words, his average processing capability is 3 cars per hour. Since Arnold is using 2 mechanics instead of 1, he has to use MM2 model. Here are the calculation result. So S1, the probability that the system will be idle will be 0.5, which is 50% of probability for 0 cars in the system. S2, step 2 is the length of the average number of cars in the system. It's 0.75, which is less than 1. And the average wait time is 22.5 minutes is given. So before it was about an hour, but now 22 minutes and a half minutes. So it's a much better improvement. And the fourth one is average number of cars in the queue, only 0.083. So the cars are kind of as they are arriving, it's being served. Almost no wait time there. And WQ, the average wait time a car spent in the queue is only 2.5 minutes with this two-line system. And lastly, the utilization factor is lambda over m times mu, and that's 33% of time mechanic is busy. So although they are not working so fully, but they are able to take care of their customers so efficiently. That's what we see here in this calculation result. And here's the comparison of the 3 options that we have discussed so far. Note that the current option, one mechanic, was running $653 as the total cost, and the second option, firing the current mechanic and hiring a new mechanic, cost the shop about $360. And now the third option is hiring another mechanic in addition to the current one. And note that the waiting cost has plunged into $33.36. So it was like $200 before, $273 before, but now $33. So waiting cost is just very minimal with this system. And daily service cost is $240. So now you are working 8 hours and 2 mechanics together, and you're paying $15 for these 2 people, and that's $240 per day. And if you add them up, that's $273. So, it's even cheaper than the second option. At the time, we were running about $360, now $273, so almost $100 cheaper than that, and the total saving will be much higher, and the efficiency and the customer satisfaction will be much higher than that. So we see that this two mechanic model is empirically we can predict that's much better than a current option, or hiring another mechanic and firing this current mechanic. So that's what we see as a result of this calculation. And now we are going to I'm going to show you how to do this calculation in Excel. It's much more complex, but I'll demonstrate how to